morning. Myself, Dr. Prashant Paude, Professor and Head, J.H. Raisoni College of Engineering, Nagpur. Friends, today we will discuss about the reinforced cement concrete. The prerequisite of this subject is strength of material and structural analysis 1. The strength of material, we discuss about the various materials and their characteristics, like stress strain behavior of steel and the concrete, which we use for the analysis and design of various components of building. So, you know, the steel is ductile material and concrete is a brittle material, but these two materials use together because their thermal expansion is nearly same. Then what type of the loading and their respective shear forces, bending moments, torsion, etc. acted on the various components of the building. So, before we proceed, first of all we discuss the IS 456-2000, which is used for the analysis and design of the reinforced concrete structures. For example, if we consider the building, there are various components, like start from the parapet wall at terrace level, the load of that transfer to beam, slab, the load of slab transfer to beam, then beam to column and column to the foundation. The IS 456-2000, there are different methods for analysis and design of the RCC structures. Very old, that is working stress method, ultimate load theory method and limit state method. But nowadays, the most popular and mostly we use the limit state method, except few liquid storage structures like water tank and retaining wall. The stress strain behavior of the various component of RCC structures is used to develop the standard equations and the methodology, which is known as given in IS 456-2000. Very well known assumption, that is stress is directly proportional to strain up to a elastic limit, that is nothing but the Hooke's law. So, first we will see the stress strain behavior of various components. Before that, what are the standards parameters which are used for designing the various components? For example, the beam, it may be singly reinforced, it may be doubly reinforced or T beam or L beam. That depends upon the requirement of the structure design. The stress strain behavior means to calculate the total compressive force and the total tensile force acted on the structures. It may be beam, it may be slab, it may be column. So, total compressive force taken up by concrete and total tensile force is taken up by steel. So, for example, if we analyze, so this is the section, cross section of the singly reinforced beam. So, B is the width, capital D is the overall depth of the beam. This is small d, we call as effective depth. This is the position of neutral axis. This is total compressive force, of course, the ultimate, and total tensile force. The stresses developed at compression zone is as per IS 456-2000 0.445 FCK, where FCK is the characteristic compressive strength of concrete at 20 days of curing. The position of total compressive force which is acted at a distance of 0.42 times XU. This is the position of neutral axis, and the distance between these two is called as lever arm. So, to calculate the total tensile force is equals to the stress multiplied by area. Force is equal to stress multiplied by area. Now, this is the force due to the steel. So, AST is the area of steel and 0.87 Fy is the stress for steel. 0.87 Fy is the stress for steel and area of steel is denoted by the symbol AST. Similarly, to calculate the total compressive force. So, the area of this section is nothing but the total compressive force. So, half base into height. So, half its XU and base is 0.445 FCK, right. So, that is finally it is equals to 0.36 FCK B into XU. So, this is total compressive force. So, total compressive force, so that is Cu. If you calculate the different factors or parameters which is required like XU, then what is the total moment required for this. So, you are taking moment about this or this. So, for this we can design the three categories of your sections. One is balance sections, second is under reinforced section and over reinforced section. In under reinforced section, the stresses of steel attain first and then concrete, and vice versa. In over reinforced section, concrete attain first, the concrete stresses attain first and then steel, right. Now, some standards required like clear cover, effective length and the various stresses. As per IS 456-2000, everything is available in various tables and various clauses, right from deflection, then limit state of cracking, limit state of serviceability, limit state of flexure and limit state of bending moment and limit state of shear forces, right. So, now to calculate the neutral axis position. So, from this diagram, the stress strain behavior diagram, you calculate the position of neutral axis. So, equating total Cu forces is equal to total tensile forces. So, 0.36 FCK B into XU equals to 0.87 Fy AST. From this you will get the position of neutral axis. So, XU equals to 0.87 Fy total area of steel divided by 0.36 FCK into width of the beam, that is B. Now, this is nothing but the actual position of neutral axis. Then, as per IS 456-2000, the calculation of XU limit. Now, this value depends upon the grade of steel. So, as per the various grades like Fe 250, Fe 415 and Fe 500, their standard equations are given. But if you consider these 456, so it is 0.48 into D. Okay. So, you calculate the XU limit and compare XU with this limiting XU with the actual neutral axis position, and then you decide the section is under reinforced, over reinforced or the balance. If XU equals to XU limit, then it is a balance section. If XU greater than XU limit, then it is over reinforced section, and if it is XU less than XU limit, then it is under reinforced section. And then you decide the moment of resistance. So, if XU greater than XU limit, it means over reinforced. So, you can calculate the total moment of resistance with respect to total tensile force. So, that is Cu into Z, and Z is equal to d minus 0.42 XU, d minus 0.42 XU, that is the distance between two forces, that is tensile and the compressive force. So, then you calculate the total moment of resistance. If it is under reinforced, so Mr is equal to C into Z, and if it is over reinforced, then it is T into Z, like this. Now, in the next part, we will discuss about the various constant, how you calculate like moment of resistance equations for that depends upon the various grades of steel. So, before that, the now this is the section, this is the width, then capital D, and this is the effective depth. Okay. Now, this is the total steel at tension zone. So, how you calculate this small d? That is equals to overall depth of the beam minus effective cover, though effective cover contains clear cover, plus half the diameter, because the tensile force is acted at CG of the steel. So, that is half the main diameter. So, this is the effective depth, you call it is effective depth. So, total tensile force and total compressive force. So, next part we will discuss about the moment of resistance value. So, that is equals to area, that is equals to area multiplied by the stresses into the lever arm. So, if it is total compressive force, that is Cu into Z, that Cu is nothing but 0.36 FCK into B into XU multiplied by Z is D minus 0.42 XU. From this we will get the moment of resistance on compression side. Similarly, you can also calculate moment of resistance on tension side, that is Tu into Z. So, that is equals to, what is Tu? 0.87 Fy into AST multiplied by the lever arm, that is D minus 0.42 XU. So, from this we will get the moment of resistance on compression side as well as on tension side. So, this is about the analysis part of the singly reinforced section. Similarly, on doubly reinforced section, T-beam section and L-beam section. Then go to the design part. In case of design, so you know the various stresses of concrete and steel. So, if it is M20, so their FCK equals to 20 megapascal, that is Newton per millimeter square, and for Fe 415 grade of steel, the stress of steel equals to 415 megapascal. Now, if these two factors are known, then you calculate the moment of resistance for these two. This is we consider the example point of view M20 grade and Fe415 grade of steel. It may be M25, M30, M35 and so on. Similarly, grade of steel may be Fe250, that is for mild steel, and Fe415 and Fe500, that is for taut steel. Okay. Now, if you consider this, so standard mu limit, you can calculate the mu limit values. If it is Fe415, then if you put all these constant in this equation, so we will get 0.138 FCK BD square. If you put in this equation, so FCK you can put 20 and B in terms of B and XU in terms of the standard, you know the XU equals to 0.87 Fy AST upon 0.36 B 0.36 into FCK into B. FCK into B. From this you put the value of XU in this formula and you will get the standard equation of mu limit. This is for balance section. This is particularly for balance section. If you change the grade, accordingly you will get the various equations. So, this is related to Fe415 grade. Then if it is Fe250, so 0.136 FCK BD square. Likewise, you go for the any other grade of steel and the combination with the concrete grade. So, next we will see in the next chapter and next lecture of course. So, thank you for today.